So first, just a little about Lua. And I really like this quote. Lua is a powerful, efficient, lightweight, embeddable scripting language that supports procedural programming, object-oriented programming, functional programming, data-driven programming, and data description, right? I think they managed to include everything there for it. But yeah. But if you look at it, it's a simple, mostly simple, rather neat little imperative language. It's got functions, so that's how you can do functional programming for it. It's extremely dynamic in the system. So basically everything is data. It doesn't, for code and stuff like this, is you can just load in a function at any time, you can delete a function, you can do everything like this at runtime while the system is running. There's no problems like this. It's lexically scoped, yes, but from the Erlang point of view, which is different, it's mutable. It has mutable variables, environments, global data. So it does mutable, shared, global data, right? Which is exactly what we don't do, any of it. And it is quite a common scripting language. It used to be in games, but it's now migrating to other things as well, too. So it's a very nice little language in its way. So this is just a very simple little code example of the testing scoping of variables. So I define the variables A, B, C, D equals 0, 0, 0, 0. I can write it like this in Lua. And that makes 4 global variables A, B, C, D. And then in this little chunk of code here, I can make local variables B, C, D, which are 1, 1, 1. And they shadow the global variables. The global variables are still there, but they shadow it. And then inside the do, I can put local variables C and D, which get the values 2, 2. And inside that do, I can make another do, which has a local variable D, which is value 3. So now I've got 4 levels of scoping here. And if I print A, B, C, D inside the internal D there, it'll write out 0, 1, 2, 3. So the A is the global, B is from the local inside the whole block, and then there's 2 and 3 local for it. And if I step out down to print 2 here, we're going outside the inner do loop there, and we're in a do, and it prints out 0, 1, 2, 2. And if I go out of that and print the 1 here, then I'm printing the ones I see from the local BCD, so it prints 0, 1, 1, 1. But the global variables are still there, but they are by default, they end up in the global table underscore G, so I can print underscore GA, underscore GB, underscore GC, and underscore GD, and I'll see 0, 0, 0. This is just a little about the scoping of the variables they have for it. It's quite a change from Erlang where we don't do scoping, right? So it's a bit different. Just an example of very simple little Lua code. So Luerl, what is it? It's an implementation of Lua written in Erlang, and it implements Lua 5.3. I think they may be probably getting on to 5.4, but I don't know if there have been any significant changes. The most significant change I've ran into was from 5.1 to 5.2 when they introduced integers. They only had floats before that. But it implements everything. Well, there are 2 things. It doesn't do a goto, but otherwise it does everything. And it implements the shared mutable global data which Lua requires. Okay. And it implements the complete handling, the Lua handling of code, which is very different from Erlang. As I mentioned, there are no concept of modules in that sense at all in Lua. They say they have modules, but it's just a way of writing things to have them. So the handling of code is extremely dynamic. You can load in a function, you can delete a function, you can change things anytime you want to while the system is running. So it's completely different handling of code. And there are other things as well too that it does for it. We have to this implementation has to work out. The major problem is actually the mutable handling data. And code, in this case, is data. Okay. So data-wise, Lua is very simple. It has very few different types of data. It's got the nil, which means basically nothing, right? Yeah, of course. It's got booleans, it's got integers, it's got floats, it's got strings, and it's got tables, and that's it, right? So if you want to have structures, you put them in tables. It doesn't have things like lists. Well, you can implement them using tables, and you can interpret them as a list, but it doesn't have it. It does have metadata, in that tables can have meta tables, which can be other things as well, and depending on how you call functions, you might end up calling the meta table instead. That's how they, for example, implement object orientation. What do you do with a class? Well, you put the class functions in a meta table, and then your instances have that as a meta table. From the Erlang side, it makes it quite easy. So the Luerl nil just becomes the atom nil. The booleans just become the atom's true, false. Integers will become integers. Floats become floats. Strings become binaries, which is basically what they are. Exactly the same thing in Luerl as well. Tables become slightly more complex because depending on the operations that Luerl requires you to do on tables, it makes it difficult to use some of the basic Erlang structures. For example, I cannot use a map. A table is just a key value. It would be very nice. It feels very natural to use a map, but I can't use a map because Luerl requires some operations that the maps don't support, which means I can't do that. So I do an array and a dictionary because Luerl handles tables or the fields of the tables where the keys are numbers. They handle them slightly special from all the other ones. They still all work together, but they have to change that, which means I'd have different ways of implementing tables, depending on whether the keys are integers or numbers or anything else. Yeah, so the key to in a table can be a table, of course. So just very quick brief here about the Luerl state we're doing here. And we need to be able to implement mutable global data we do that with immutable local data. So the Luerl state is a big structure which you pass around when you're working with it. It's just a normal Erlang data structure for doing this. And we keep it all in one. We explicitly thread this through, which means you can run lots of different Luerl states by just having different structures. And they're completely private to each one. And there's a global table store. There's a global function frame store as well too, because that's sometimes needed depending on how the access you're allowed to do with the local variables in functions. So they're nested as well too. You can do some really weird stuff there. That's the environments for doing that, because sometimes you can have your nested functions internally, and a function further down can actually go in and change the local variable of a function further up in the state. Not only just read it, but it can actually go in and modify it as well too, which can give you some quite fun things to do for it. There is also user data, which is local data to whatever implementation it does here. So in the user data, I could put Erlang data structures. So the thing is, when you reference all these, I might have a user data, which I go in and modify, but everyone else will be accessing the user data thing as it was there before, which the data has changed for it. So I have to put that in the same way as doing state for it. And this also means we have to implement our own garbage collector for this local data state. Of course, all the Erlang data structures that are freed and so on, we leave those quite naturally to the Erlang garbage collector, but we have to do our own garbage collector of our state here. So this is just an example. This record is the Luerl state, right? So it's got tables, it's got environments, it's got the user data, it's got the function table as well too. So I can create a function, I can put it inside a table, and I can access it through the key, but it's somewhere else. And if I use that, I can use that function and have multiple reference to it in one place from different places, right? And G here is the global table. This was the underscore G we saw from the beginning, which is a global table, which is the top level. Everything else is below that table. So if you want a table, there's a table called there's a set of functions called OS for working on the surrounding operating system around it. They're just they're in the global table under the key OS. You've got the separate hierarchies down there. We've got the current stack. This is the stack while we're evaluating the functions for it. Yeah, I mentioned they're meta tables. So a table can have a meta table, but there are also meta tables for the various built-in data types. So there are four data types here, right? So there are meta tables for integers, for floats, and for strings and things for it. So I can use metadata for those as well. And there's specific ways of calling, so you can end up using the meta table if there's nothing there. We need a random state. That's just in the random there. We need a unique tag as well too. So I can throw things, I can safely throw things and catch them later on by using that tag in there. So every table has its own unique tag. And I can do trace functions as well. This is just default values. None means I'm not tracing anything. And I can put data, trace data functions can put data in the trace data and pass them around to the trace functions. The bottom one here, the struct is, this is how the first four, the tabs, the ends, the USDs, and the funcs handle their data. Because they have to be able to be garbage collected and dereferenced and be garbage collected. Now, one way to do that would be, which I sort of do, is that I just give an index to one. So the first table gets 1, then to 2, then 3, bump, 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 all the way up like this, that's fine. And then when I garbage collect it, I'll find I've got no more references to table number 39, and they will just be removed from the whole Luerl data structure, and it won't exist anymore. The trouble with that is that it can be very easy, I think, to run out of integers and stuff like this. So I want to be able to reuse the integers. So the data field in the T-struct, that's the actual data. The free, that's a list of the integer values that aren't being used anymore, and the next is the next one if there's no frees for it. This is just how the garbage collector works, right? So if it finds a table is no longer in use, it just removes that and puts the number in the free list and things like this for it. That's what this is doing. But again, this is just because we have to handle our own garbage collection, our own managing of data, dynamic managing of data. And it's exactly the same thing for all the first four levels. So the same thing with functions. When I call a function, I might be calling function 39, which will then go in and look in the data structure and find function 39 and use that, for example. And that can be used in many different places. And one user might change that to use another function, but the other users might still be using the same values, the same function. So it's extremely dynamic and very, everything's very data-oriented in that sense. So that, of course, affected the implementation. Basically, it's quite straightforward. There is a compiler which compiles down to a Luerl, a VM, and I've implemented, Luerl instructions, and I've implemented a Luerl VM for implementing that. It's a stacked machine, yes. Arguments and calls, they're passed in a list, because Luer doesn't have any specific, I can say how many arguments I'm going to make in a function call, but I can give more arguments and they're kept, or I can have fewer arguments, in which case the values just get the default value nil, right? So you always have to know when you're calling how many arguments you've got, and then it's a function's job to work out what to do with these arguments. And the same thing with return values. So I can return no values, equivalent to nil, or I can return one value, I can return 10 values. And it's up to the caller to decide what to do with the return values and how many it gets back. Therefore, we're just returning lists. And you can, from inside, call functions which will result in calling Erlang functions. This is how you can get out of the Luerl system for doing that. And you can make Erlang calls for doing this. This means, well, the extra special handling of frames and environments, that's just because you can update the various frames and call argument lists and stacks and stuff like this while the system is running, which means I cannot just use a normal list because I have to update it and just starts getting very complex. That's that part. This also means that Luerl can be sandboxed. Because I do everything in the Luerl VM, I have complete control over what I call. And which means that there is no way from inside Lua to load in something which goes outside the system. Okay, I can only call things that are defined in. I can define Lua functions, but they cannot get outside the system by default. The only way you can get out is from the outside. You can go in and say, yeah, if I call this function in this table, I'm going to end up calling this Erlang function and do things on the outside well. It's the same thing with the user data. Luerl can pass Lua, and Luerl can pass the user data around, but has no idea what's going on inside it. We just use that. So it's possible to sandbox the system. I can go from the outside and say, I want to block all these calls going out. And from inside, I can't change that. So this makes it one difference from running Erlang or Elixir code, which can't be sandboxed. But here you can sandbox things. It's quite simple to sandbox it. And again, if it's sandboxed, if I don't from the outside allow the Lua code to change things, I cannot do that, right? So in that sense, it's a very nice little thing for doing this. Sandboxing, of course, you can do that with any language you implement yourself. We have complete control over what's going on inside it. But I mean, once you compile down to Erlang or even run the Erlang abstract code, you lose that control, and then you can get out. And yeah, that was about all I'd planned to say on Luerl. I'll be giving a slight demo this evening, well, later on in the The lightning talks, yes, about controlling spaceships with Lua for it. But that's more fun. Okay, sorry, that's me anyway. So I'll hand over now to Dave, who will talk about doing it in a real use for it.
Hello, Robert.
Hello, Dave.
Always wanted to say that. Hello all, I'm Dave Lucia. I'm CTO of an early stage startup called TV Labs. We are transforming the way that media companies develop and test smart TV applications. And thank you to Robert. It's an honor to be on stage with you for building Luerl. And I'm going to tell you a bit about how we use it at TV Labs. All right, so raise your hand. How many of you own a smart TV or a set-top box like a Roku or an Apple TV? Pretty much everyone, right? All right, sorry. So testing for all of these apps is very hard because there's so many different types of devices. And the way that media companies do this is with a physical room of televisions called a TV lab. A TV lab, people will actually walk up to and upload their build with maybe a USB stick and poke around the application and test different workflows, certify releases, etc. You can imagine this is slow, cumbersome, and a bit expensive to do at scale. So our solution to this is to virtualize physical devices and make it available through your web browser. So with our product, you can go out, you can check, I want a very specific LG television. We then pair you with that television, and then you can interact with it in your web browser as if it was right in front of you, including the ability to sideload apps to it, and then use vendor-specific SDKs to open a Chrome web debugger or anything else that you might want to do. And then we have a command line interface that makes it really easy to do all this as if it was right on your local network. So on top of that access product where you can interact with the TV, we layer on top automation. So our codeless automation tool lets our customers write test cases in a no-code format, and using computer vision, our product allows you to use text, color, structure, semantic data, navigate between screens, and make all these different types of assertions. And so this lets people who are not developers really quickly put together test cases and workflows that can then be run on any different type of television or set-top box. All right, so this guy's wearing a sport coat and he's selling me his product on stage. I thought we were talking about Lua. So yes, we do use Lua, and when we were originally building our product, we needed a way, just a prototype. How could we possibly automate something on a television? We are running Elixir in our web cloud platform, and then on our edge devices that run with our televisions, we are also running Elixir. So naturally, something running in Elixir would be a good fit. And when we found Luerl, it seemed like an obvious choice for initially building a prototype. With the added benefit that, as Robert said, you can very easily sandbox Luerl functions. You can not expose certain parts of the API. You can extend the API with any sort of DSL written in Erlang and Elixir. And this was just a really good solution for us. So our product works a bit like this. A user is going to write a Luerl script, or possibly even just use our no-code drag and drop workflow tool. They then pick a device or a range of devices that they want to run their code on. They request execution. Then our platform is tracking all of our available devices. It matches them with a set of devices. It sends the script and any execution context down. And then we start executing the code on the device, or I should say on the NVIDIA Jetson, which runs with the device, all in Luerl. As it's executing, we emit events that are then Phoenix pub subbed back up to our platform. We also stream back video, screenshots, and we use this to power a host of different UI and other affordances to know what's going on with your script. So show, don't tell. I'm going to do a little video that I recorded. Hopefully it loads.
Hello. In this video, we'll be using the TV Labs automation platform to open up the ITV app, navigate to the settings page, and validate that our postcode is being displayed. To start, let's upload a screenshot of the ITV homepage. In order for TV Labs to know what page it's on, we need to give it some visual cues. So let's pull out this ITV logo, and using our color matcher, we're going to pull out that dominant yellow and make sure that's within 10% of that color. Great. That's enough to recognize the home page. Let's recognize the settings page. I'm going to pull up a screenshot of the settings page like we just did for the home page. And this time, I'll use this location tab on the top left. And using our text recognition system, we'll make sure that the text location exists exactly in that part of the screen. Cool. So now we can recognize the settings page. Let's also make a region for the postcode. Because the postcode is going to be a separate validation, we won't make it part of the required regions for detecting that this is the settings screen, but we will check that the text postcode exists. Awesome. That's all we need to do to mark up the screens. Let's build a workflow now. We'll start by opening up the ITV app. Once it's open, we need to wait and make sure that we've launched and loaded onto the home screen. We'll give it 20 seconds, and we'll make sure that it's stable for 3 frames. Now we need to navigate over to the sidebar, go down to the settings label, and hit enter. So we're going to go left to the sidebar, down 1, 2, 3, 4, 5, 6, 7 times, and hit enter. We'll give it 100 milliseconds of latency in between each press just to make sure that the system is processing them. Now we'll wait for the settings page, waiting for 3 stable frames like we did before. And finally, we're going to assert that that postcode region does exist and has the postcode inside. Cool. Let's run trace, and we're going to run this against an LGC3. What's happening now is that TV Labs is pairing me with a physical LGC3 inside the TV Labs data center. This is going to start executing, and it will send down this workflow and run each step, which you can see that it's doing right now. So for each step, we can see visual cues about what is happening on the screen. Cool. It's located the ITV app. It's navigated down to the settings tab. It's loaded up the settings screen. And it's asserted that the postcode does indeed exist on the page. Awesome. We built our first workflow.
Doesn't want me to go to the next slide. Come on. There we go. OK, so hopefully that demonstrated a bit of how the product works. Now, the key thing here is when you're dragging and dropping those workflows, it's actually taking each one of those steps and generating Lua code. So we have print at the very top here, hello code beam. And you can see on the output on the right side, you see the print hello code beam. Before and after, we have a bit of boilerplate that we generate that emits events as the steps are executing, and provides a little bit of metadata about what's happening in each step so that previous or subsequent steps can reference data and output from the previous steps. Events are emitted as the workflow is executing, and that allows us to put logs on the left side there. Actually, that could be expanded for more information. The workflow itself shows errors, and then screenshots are available on the right-hand side. Now, this is just our trace view. We actually have a more robust debugger view, which gives you a timeline and whatnot, and then just a kind of more broad aggregate one for if you're running many different workflows across many different devices and just want to see, did my test pass or fail? So in order to do this, we write a bunch of Elixir functions and then expose them as Lua. So we can see on the left-hand side that I'm printing device info, I'm power cycling the device, I'm launching the Netflix app. And the way that we express this in our application is with this Elixir module on the right. Notice I'm using lua.api and giving it the device scope. And then any function that is written with def Lua just gets exposed as a Lua function underneath that scope. And I just write my normal Elixir code, and things like maps, like you see in the info function, are represented as Lua tables. And this all happens for you under the hood automatically. There's also some decorators that you can provide to functions. As Robert said before, functions are variadic by default in Lua, meaning that you could pass any number of arguments. I inverted that default behavior so that I could more naturally express Elixir functions. But you could turn that off if you want to support that, or if you don't want your program's crashing if a user provides an extra argument you didn't expect. So in our product, we have LLMs and AI that allow you to take a frame and hand it over to the LLM and ask what's on it and get structured data back. As you saw in the demo, you could do text recognition, keyboard input. You can use remote control through IR, CEC, or any of the vendor-specific APIs. For example, if you're on a Roku, you can use the Roku API to communicate. We have high-level APIs for waiting that a screen loaded or waiting that motion has started on the screen on a particular region in the screen. You can wait for playback to start. You can throttle the network, record metrics, upload assets, and many other things. So when we were originally starting with Luerl as a prototype, we realized, oh, actually, this works really great, and we got some traction here. Let's keep it going. So in order to be able to provide very high-level APIs and DSLs, I wrote a wrapper library around Luerl, aptly named Lua. What this provides is many things, including a sigil, Lua, that actually will parse your Lua code at compile time and tell you if there's an error. So you can express Lua code in your Elixir code with the Lua sigil, and then if you accidentally forgot an parenthesis or whatever, you'll get an exception with a stack trace in your Elixir code. It has the ability, as we just saw on the previous slide, like this. You can use Lua API and then write these def Lua functions, and then you can load them into your scripts. Various utilities for working with tables to transform them into more semantic data structures in Elixir. Additional sandboxing primitives. Deep setting and getting of variables and state, excellent documentation, improved error messages, blah, 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 a lot more. So we use this heavily for everything that we're using Luerl for. So overall, Luerl has been, I think, a really good success. Again, we started as a prototype, and now we keep extending it, building more, and now we've pretty much fully abstracted away Lua itself, and we're preferring, even for our own internal usage, where we write maintenance scripts to run on all of our different devices, we're writing those in that high-level workflow, but Lua remains this really good glue language that is sandboxed, has these DSLs, is a really good target for LLMs, for generating code. And I think the biggest thing is that it just reduces operational complexity. So rather than having some sandbox Docker container where I'm running JavaScript or Python and then maybe some like HTTP thing for any of my DSLs that I want to run, or God forbid, writing them in Python or JavaScript, we can write that all inside of Elixir, and it works really well. So now that I have Robert on stage, I can pressure him into my feature list request. So the things that I think we can improve in Luerl and that I'm also trying to help with are continuing to improve error messages and stack traces. There's certain things where, for example, if you try and call a function that doesn't exist, you don't always know exactly what symbol you are referencing. So things like that, there's still work to be done to be improved. Getting Luerl on hex docs. I have a PR open that Robert and I, maybe later today, we'll try and work through. And then some of the APIs in Luerl could be consolidated. So if you want to try Luerl yourself, I have a lofty goal of rebuilding the luerl.org website. But for now, you can try and type this somewhat confusing link and test out Luerl for yourself. I have a few different examples of Fibonacci, a Hello Robert program, and a weather API, which actually makes HTTP calls. And you can look at the code underneath the hood to see how that all works on that link right there. So with that being said, we have a couple minutes for questions if we want. Otherwise, thank you very much.
This will not disable itself, but it did. We actually got one question from Uwe. Can the user of TV Labs system write their own Lua code, or should they use flowcharts that generate the Lua code?
So our initial version, we were pushing you towards using Lua code. I don't think anyone really wanted to write Lua code, especially because the people who are our customers are not always programmers. And if they are programmers, they might be working with actually somewhat more esoteric languages, one of them called BrightScript, for example. But they're probably more familiar with JavaScript or Python. So you can write Lua. We allow you to do it. We don't. It's not that we don't recommend it. It's just much easier to use our drag and drop high-level visual programming tools.
Thank you so much, guys. I guess you will be around if people want to find you and ask questions. And with that, thank you so much. It's a pleasure to have you.
Thank you.